Okay, so we are going to use our free body diagrams to solve some conceptual problems. So this is using free body diagrams to solve conceptual problems, and there's 3 questions within this daily practice. So the first one reads, a person is riding in an elevator while standing on a bathroom scale. They look down and see that the scale is reading less than their weight. What direction is the elevator heading? Note, the scale reads the normal force. So we're going to remember that as we do elevator problems and the idea of elevator problems, which is this whole sort of daily practice, that the scale on the elevator reads the normal force. So I'm going to try to fit all 3 of these in here. The first problem is the object you are standing, or the person standing on that elevator. So there's our person. If we want to draw our picture, you can sort of think of, here's the floor of the elevator with the scale on it, and that's really where the interaction is happening, and then of course we have the person. Okay, so we need to think about our interactions and at the same time draw that free body diagram to see if we can use it to conceptualize our motion. It tells us that they look down and see that the scale is reading less than their weight. So what is actually interacting? What are the forces acting on this person in the elevator? Well, we know that there is the force of gravity. And that's between the person and the earth. And the force of gravity acts down. So we have the force of gravity equals mg equals the weight. And this is what's going to be important. The force of gravity is the weight. The weight of the person is the weight of the person. It's the true weight of the person. Now this person is standing on a scale, so the scale is also interacting with that individual, and the problem gives you that hint. It says the scale represents the normal force. We could write the force of the scale that equals the normal force. That is what the normal force is in this situation. We're squishing the scale, like we squish the molecules of the scale. So we have the person and we have the scale. Now, it tells us that the scale reads less than the person's weight, less than their weight. This is their weight. The length of this arrow is their weight, true weight, mass times gravity. So if the scale reads less, should the arrow be bigger or smaller or the same size? Well, it should be smaller. If the scale reads less than their weight, then it's going to give us a smaller number than the weight, and that's represented by a smaller arrow. So this is how our free body diagram looks like. Now what can we use that information for to say something about the motion? Particularly, what direction is the elevator headed? Just says they're riding in an elevator. Okay, well, one possibility is that they're heading up, and the other possibility is that they're heading down. So does this free body diagram give us that information? What does it give us? It tells us that the up arrow is smaller than the down arrow. So the net force is in what direction? Well, if I add these 2 arrows together, the net force is down. So the sum of the forces, and we're dealing with vertical forces, is negative. The sum of the forces is negative. Now, can a person be traveling up and have a negative let's back up once. If the sum of the forces is negative, this tells us that the acceleration is negative. All right, so now let's think about that acceleration being negative. This picture gave us the idea that the sum of the forces was negative. The sum of the forces is negative tells us the acceleration is negative. If a person is traveling up, can they have a negative acceleration? Yeah, they can. It means they're slowing down. So one possibility in this scenario is that they're traveling up and slowing down. All right, so maybe they're traveling up. Well, the other question is, can they be traveling down and have a negative acceleration? Yep. So what happens then? Well, then they're speeding up. So they could also be traveling down and speeding up. Well, it doesn't tell us anything that it's less than the weight. So just by looking at the acceleration does not tell us direction of motion. That sounds awful familiar to our last unit. where the direction of motion the direction of acceleration doesn't tell us anything about direction of motion. So the net force tells us the direction of the acceleration, but it doesn't really tell us about direction of motion. So this question is unanswerable. The direction can't be determined. It could work either way. And we want to think about how that works, what those two either ways should really look like. If it's traveling up, and this is the scenario, if you're traveling up and the scale reads less than your weight, well, then you're slowing down. And that happens. If you're traveling up in an elevator and you're coming to a stop, you sort of feel a little lighter. The scale actually is going to read less than your weight. If you're traveling down and you're speeding up, well, that's when you feel a little lighter too. You're at the top. You're going to start going down and speeding up. You sort of get that feeling in your tummy, feel a little lighter. The scale is going to read less than your weight. So we cannot determine direction on this one. Not intended to be a trick question, but intended to get you to think about it. Can direction be determined? All right, let's try the second one. Number 2. Number 2 says you are lowering a bucket down into a well. Is the tension of the rope on the bucket greater than, less than, or equal to the bucket's weight if, as you're lowering it, it's coming to a stop? So now we have some more information. All right. So our object is going to be the bucket. Our object is going to be the bucket. So if we draw a picture, we have, here's our bucket and the string. I'm not the best artist. Now let's think about our interactions. I'm going to hold off on the free body diagram for a moment. And let's first look at our interactions. Well, we know that there's gravity. So we have the force of gravity, and that's going to be between the bucket and the earth. That always acts down. Now the bucket is being lowered down to the ground, so we also know that that string is attached. So we have the force of the string. Again, we might call this a tension, T for tension. It's strings, rope, cable. And that's between the bucket and the string. And that's holding that bucket up or keeping it up. Tension is in that upward direction. Now, are there any other interactions? I'm holding on to it. Oh, but I'm not really touching the bucket. I'm just touching the string. Nothing right or left. I think that's it. So those are our 2 interactions. Now let's think about what the problem tells us about those 2 interactions. We can start with our free body diagram of the bucket. We know that the force of gravity is a property of the bucket itself. All right. So how big do I draw that tension arrow? That's all what the question is asking about. Is the tension a bigger arrow, a smaller arrow, or an arrow of the same size? So let's look at it. It tells us that the bucket is moving down. So we know that it is moving down. It also tells us that the bucket is coming to a stop. So it is slowing down. And from our last unit, what does that tell us about the acceleration? Well, when something is slowing down, direction of motion and direction of acceleration are opposite. So there's those chances to pause the video and check yourself. So if the acceleration is opposite motion, this tells us that acceleration is positive. If the acceleration is positive, the net force has to be positive. And these forces are only in the vertical direction. Also has to be positive. If the net force is positive, the up arrows have to be bigger than the down arrows. So how do I draw my string? I have to draw it bigger than the force of gravity. A bigger up arrow than down arrow tells me that the net force is up. Net force up, positive, tells me the acceleration is up or positive. If I'm moving down and I have a positive acceleration, then I have to be slowing down. That's what the problem tells me I'm doing. So it all works out. All right, using these ideas just to conceptualize what is happening, let's try the third one. The third one says you are raising a bucket out of a well. Is the tension of the rope on the bucket greater than, less than, or equal to the bucket's weight if you're raising the bucket at a constant velocity? Okay, well, we got our bucket again. So if we think about our object, It's the bucket. Let's draw our picture. Whoop, there's the string. Okay, what are the interactions that are happening? So again, we're trying to think about those different interactions. We know there's gravity, so we have the force of gravity. That's between our bucket and the earth. And if we start to develop our free body diagram, oh, forgot my bucket was pink. There's my bucket. We know that the force of gravity is always pointing downward, and that's a property of the object. So it's going to have a very specific length of arrow equal to mg, which of course is defined as our weight. Okay, what's the other interaction? Well, we've already talked about those interactions, what does and doesn't exist, and we learned that there is also the force of the string, which we call the tension, and that is between the bucket and the string. And that points up. All right, so the question is, how big do I make that arrow? How can I conceptualize the problem and use it for my free body diagram? Well, it tells me that the bucket is being raised at a constant velocity. So what information do I have? Well, I have that the bucket is in the upward direction. Constant velocity tells me the acceleration is 0. If the acceleration is 0, what does it tell me about the sum of the forces? They're also 0. If the sum of the forces are 0, the tops have to be exactly equal to the bottoms. And there's only one up arrow, and so that one should be exactly equal. Make it a little bigger head to the bottom. So these two are meant to represent the same length. If the two arrows are the same, the net force equals 0. If the net force equals 0, there's no acceleration. If there's no acceleration, constant velocity, and that's what the problem tells us. If, instead of going up, the bucket was going down, would anything about the problem change? Pause, think about it, and answer why. All right, no, nothing about the problem would change. By looking at this free body diagram, we can't tell whether the bucket is going up or going down. We know it has to have no acceleration, so we actually also can't tell if it's staying still or moving at a constant velocity. So this free body diagram gives us information about the acceleration, and the problem gave us the rest of that information. Okay, so lots of practice on drawing free body diagrams, really seeing if what the problem is doing, that's what this daily practice is all about, is what the problem and describing in terms of the motion match how our free body diagrams look. Can our free body diagrams used to explain what the problem is doing? All right, good job.